Welcome to this explainer. Okay, I am literally so excited to get into this today because we're looking at something that honestly sounds like total science fiction at first glance. We are living in this wild moment where two massive tectonic plates of technology are just smashing together. On one hand, you've got this absolute explosion of AI hardware, chips that are designed specifically to run neural networks as fast as physically possible. And then, on the other hand, we have the looming threat of quantum computers, which is forcing the entire world to upgrade to some highly complex post-quantum cryptography. So what if those two completely different worlds could perfectly overlap? Today, we're exploring the cutting-edge concept of verifying a NIST standard post-quantum cryptographic signature using absolutely nothing but standard neural network operations. We're talking about taking the absolute highest level of modern security and running it natively through the exact same mathematical pathways that power modern AI. And that brings us to this seemingly impossible question posed by our recent foundational paper from the legendary cryptographer Adi Shamir and his team. Now, just to anchor how massive this is, Shamir is literally the S in RSA cryptography. When he and his team ask a question, the entire cryptography world stops and listens. And the question is, can a standard neural network actually be a cryptographic implementation? We're not talking about an approximation. We're not talking about an AI trained to sort of guess if a signature is valid. No, we're talking about a mathematically flawless, perfectly secure implementation of cryptographic verification using only neural net architecture. Literally the exact same architecture used by things like ChatGPT or your favorite image generators. So here is our roadmap for today. We'll start with crypto inside a neural net, then check out the ML entry ticket, break down the mathematical magic trick, see how we go about surviving the fractional attack, and finally wrap up with unlocking massive GPU speeds.
All right, let's jump right into step one, crypto inside a neural net.
So this entire exploration builds on an initial paper by Shamir and his team. It's IACR ePrint 2025/288 if you want to look it up, which explored how to securely implement symmetric crypto primitives in deep neural networks. But what we're looking at today raises the stakes massively. They applied that framework to something way more complex, FIPS 204 MLDSA 65. That is the official US government NIST standard for post-quantum verification. The goal here? To take that incredibly rigid cryptographic standard and verify it using only the three operations a neural network actually has: addition, multiplication by a constant, and the ReLU activation function. For anyone newer to the AI side of things, ReLU, or rectified linear unit, is basically just a mathematical filter used in AI to introduce nonlinearity. Trying to force high-level post-quantum crypto into just addition, multiplication, and ReLU, it's practically like trying to build a working supercomputer out of just three specific types of Lego blocks. And the kicker? It has to be exact, it has to be safe, and it has to be blazingly fast.
Moving right along to part two, the ML entry ticket.
Now, you might be wondering, why go through all this trouble? Why do we need to force standard, highly optimized crypto code into a neural network structure in the first place? Well, it really comes down to getting access to the computing VIP lounge. We've got these incredible new technological environments right now. Think about fully homomorphic encryption, or FEG, where we can compute on encrypted data without ever actually decrypting it. Then you have zero-knowledge proof systems, letting you prove you know a secret without ever actually revealing what the secret actually is. And of course, dedicated machine learning accelerators like NPUs that are popping up in literally every single device. These environments are incredibly powerful, but man, they are incredibly strict. They will completely reject traditional computer code that uses branching logic, like simple if-then statements or table lookups. Why? Because branching logic just completely breaks their underlying math. If you want into this VIP lounge, you can only speak one language: arithmetic circuits, which means matrix multiplication and activation functions. So traditional cryptography, it just gets bounced right at the door of these advanced hardware systems. Expressing cryptography purely as a ReLU circuit is really the only way to sneak it past these specialized hardware bouncers. We aren't actually changing the hardware to fit the cryptography. Instead, we're cleverly disguising this incredibly strict cryptography to look exactly like machine learning, so the hardware just lets it right in. It translates the crypto into a native language that these next-gen chips understand and can accelerate.
Which brings us to part three, the mathematical magic trick.
Okay, this is where the true mathematical magic happens. Cryptography requires perfect, discrete logic, absolute ones and zeros. Neural networks, on the other hand, use continuous math. They rely on fractions and approximations, which, is great if an AI is trying to guess if a picture is a cat or a dog, but it is absolutely fatal for cryptography.
So how do you bridge that gap? You use what the researchers call the ReLU gadget. By carefully arranging just two neurons, you can create a perfect 0 to 1 step function. But here is the absolute genius part. A standard ReLU activation function has this slanted ramp, right? That slanted ramp represents all those continuous numbers and messy fractions. If you land on that ramp, you get an approximation. But because the MLDSA cryptographic scheme relies entirely on whole integers, the inputs will always step perfectly onto the flat parts of the graph. They mathematically leap completely over the unpredictable slanted ramp, landing safely on the flat, predictable steps. It guarantees exact, flawless logic with zero messy approximations. And from that one brilliantly simple two-neuron trick, a whole world just opens up. By chaining these gadgets together, the researchers were able to construct every single discrete operation that the super strict FIPS standard requires. It's essentially building a Turing-complete toolset out of just two neurons. You can build floor division, you can build modulo arithmetic, you can even build XOR and Boolean data selection. The whole shebang reduces back down to that perfect, predictable 0 to 1 step from the ReLU gadget. But, there's actually a beautiful sort of serendipity to this approach, specifically when we're talking about modern post-quantum cryptography. MLDSA is what's called a lattice-based cryptographic scheme. Its absolute heaviest, most mathematically intense step relies heavily on multiplying a giant fixed matrix of numbers by a variable vector. Well, in the AI world, a fixed matrix multiplied by a variable vector is literally just one linear layer. It's a match made in heaven. It is the exact mathematical operation that neural networks were born to natively crush. Because of that lucky break, the heaviest part of the crypto requires zero special gadgets and takes absolutely zero extra computational cost. And the exhaustive validation they ran is the ultimate stress test to prove this actually works in reality, not just as theoretical math on a chalkboard. The researchers checked over 8.3 million field values for the decomposition and rounding steps directly against the official FIPS reference library. And the result? Coefficient for coefficient perfection. The Shake 256 hashing circuit? Byte identical. And just to be clear, byte identical means the neural network isn't hallucinating or approximating a signature at all. It is acting as a mathematically perfect calculator, identically matching the official US government standard. The full verifier successfully processes real MLDS signatures, perfectly accepting the valid ones and completely rejecting the tampered ones. But, this is cryptography, so we always have to assume the worst. Let's look at part 4, surviving the fractional attack.
So what happens when an attacker decides they just aren't going to play by our neat little whole integer rules? Remember how our ReLU gadget relies on integers safely leaping over that unpredictable slanted ramp? Well, an attacker could maliciously feed a fractional real-valued probe into the network, say the number 0.37. By doing this, they're intentionally forcing the network onto that slanted ramp. This essentially lets them slide right past the math locks, creating a sneaky backdoor to bypass the verifier entirely. In a naive implementation, this is a fatal vulnerability. A vulnerable verifier blindly accepts these fractional inputs and just fails. But Shamir's team implemented an incredibly elegant fix to create a safe verifier. With literally just one single extra neuron, they built a trap. The network sanitizes the input, forcing every single input to snap strictly to a 0 or a 1. If an attacker tries to sneak in a fraction, the network detects the deviation, calculates a penalty, and then aggressively subtracts that penalty from the final output. It mathematically crushes the forgery attempt before it can even finish processing. All right, so the math is perfect, the network is totally secure. Let's get into part 5, unlocking massive GPU speeds. Now, running this on a GPU sounds like a total no-brainer, right? GPUs are parallel processing monsters. But there is a massive engineering hurdle here called the precision problem. GPUs want to run fast, so they naturally accumulate their matrix multiplications using a format called float32. Think of the GPU's memory kind of like a calculator screen that can only fit 8 digits. If the math generates a massive 12-digit number, which this lattice cryptography does constantly, the GPU just chops off the end and rounds it out. In AI, rounding is totally fine. In cryptography, rounding means catastrophic failure. Float32 is mathematically exact only up to 2 to the power of 24, but our calculations reach massive numbers like 2 to the power of 54. To solve this, the researchers used a super clever workaround called limb decomposition. It sounds a bit like biology, but in math, limb decomposition basically means chopping that massive overflowing number into smaller, bite-sized pieces that perfectly fit inside the GPU's safe limits.
They process these limbs so that the partial sums strictly stay under that safe 2 to the power of 24 threshold. Once the math is done perfectly on the GPU without any rounding whatsoever, they recombine the results modulo Q. It keeps the math perfectly exact while completely unleashing the raw, parallel power of the hardware. And the payoff for all this engineering is absolutely staggering. Just to put it in perspective, a pure Python reference implementation verifies about 150 signatures a second. Highly optimized C code running on an 8-core CPU can push out maybe 23,000 verifications a second. But by running these perfectly precise, secure relay circuits in massive batches directly on a standard laptop GPU as a neural net, they hit a blisteringly fast 120,000 verifications per second.
So let's just take a second to reiterate why these three pillars are essentially the holy grail here. First, we have a system that is exact, with absolutely zero approximation. Second, it is safe because the Shamir sanitization completely closes the door on fractional attacks. And third, it is incredibly fast. Now, maintaining an authentic sense of discovery means being completely impartial and honest about the constraints of where the science is today. This setup is currently for verification only. Actually doing the signing would require baking the secret key into the neural network weights, which just isn't safe right now. And currently, the public key is baked right into the network structure itself, meaning it's one key per network. Those are the honest limits of the implementation as it stands today.
But even with those constraints in mind, it is truly a masterclass in seeing the hidden compatibilities between two completely different fields of computer science. As the authors perfectly put it, the hardest part of this crypto is what AI does natively. Everything else is just comparators. It leaves us with this massive, provocative question. If we can perfectly run the world's most advanced post-quantum security natively inside a standard neural network, what other impossible computational walls are about to fall? Thank you so much for joining me for this explainer, and keep exploring.